What's up? I'm Vin, and today I want to go through the January 2024 Geometry Regents, and I'm going to go through parts 2, 3, and 4. I'll leave a link to a copy of this test in the description below. But first up, we're going to do the part 2 questions, and each question here is worth 2 credits. Question 25, we have isosceles triangle ABC, and we're told that line segments AB and AC are congruent. So we're just going to mark these off as congruent. And then next we have altitude AD is drawn. Well, if AD is an altitude of this triangle, and it hits this side over here, we could say that these two angles here are 90 degrees. And then next we have the length of AD is 12 centimeters. So I'll just label this over here as 12. And we have the length of BC is 10 centimeters. And that means we can mark this 5 and 5 like this, because we were told that we have an isosceles triangle and the altitude is being dropped down to the base like this. So that's going to bisect line segment BC. So for the actual question, we have to determine and state to the nearest cubic centimeter the volume of the solid formed by continuously rotating this triangle about line segment AD. So what we have to be able to imagine here is which solid is formed if we rotate this triangle in a horizontal direction like this about line segment AD. The solid formed would be a cone. So I'm just going to draw out, we would have a cone here. And if we think about the dimensions of the cone, we have to use the triangle to help us fill out the dimensions. So I just imagine point A would be up here. Point D would be right in the middle of this circle at the bottom here. And let's say I have point C over here. I'm just freezing time for a moment and saying if this triangle is just rotating continuously, I'm just looking at one slice here like this. So this would be, let's say, ADC like this. We could imagine going to the diameter across like this. This would be point B. And then I could draw this line segment like this to give us the entire cross section. But I only need to consider one of these pieces or one of the right triangles here. So we were told that DC is 5 units long or 5 centimeters. And this, once again, we concluded from saying that the altitude is going to bisect this side over here. So I could say that this piece over here is 5 centimeters, but we'll leave the units out. For this part of the regions, you can leave the units out of your answer. It's not going to count towards your full credit. So you can, once again, just leave that out. And then next we have that the altitude or the height of this cone is 12 centimeters. So we have the radius is 5 and we have the height is 12. And for the volume here, the volume of a cone is 1/3 pi r squared times h. So all we have to do here now is just plug in. We're going to have volume equals, we have 1/3 pi. And then r is 5, so we're going to do 5 squared times h is equal to 12. And the rest is calculator work. So let's type this in. We have 1/3, and I'll just write this in parentheses. And then we have pi is second and this up arrow here. And then we have r is 5, and we're going to square this and then multiply by 12. And remember, in math, parentheses means multiply, so we could just type it just like this in the calculator. And to the nearest whole number here, we're going to have 314. So to the nearest whole number, our volume is going to be 314 cubic centimeters. Now, once again, you do not lose points if you do not write units. The reason why I would advise some students to leave the units out is you could only lose points if you try to write the units in, but you do it incorrectly. So here, our final answer technically would be 314 cubic centimeters, which would be centimeters to the third power. And I'll just make that a little bit neater. So we have centimeters to the third power. So if you want the concept of how do we get cubic centimeters, the radius is 5 centimeters and it's being squared. And then we have the height is 12 centimeters. So note here that we have centimeters to the second, and then we have centimeters to the first. When we multiply centimeters to the second by centimeters to the first, we're going to get centimeters to the 2 plus 1 or centimeters to the third. Okay, so we have 314 when we round to the nearest whole number, but the units here, this is how it would build up to cubic centimeters. But once again, for the regents, in the free response, you do not lose points if you don't write units. So this would get us full credit. Question 26, the diagram below models the projection of light from a lighthouse L. And the sector, that's the $1 million phrase right here, has a radius of 38 miles and spans 102 degrees. And we have to determine and state the area of the sector to the nearest square mile. So for this question, the concept that we need is we have to understand that a sector is a section of a circle. Okay, so if we're thinking about a circle, so let's say we're just imagining some circle here, and let's just make this neat. So we have some circle, so there's our circle. then what we could do is just section off a piece like this. So I'm going to focus on this piece. And this models what's going on in the question. So what we have to find here is the area of the full circle. So let's pretend here that first we're finding the area of the full circle if we weren't just taking a section that cuts off 102 degrees. Well, the area of a full circle is pi r squared. So we would just do first, we would have the area equals, and we would have pi times the radius squared. And we were told that the radius is 38 miles. So we'd have 38 squared like this. But this would be the entire area of the entire circle. If we want to think here, what fraction of the circle are we taking? Well, if the central angle is 102 degrees, we're taking 102 out of the full 360. Okay, because a circle goes a full 360 degrees, so we're just taking this much out of 360. So now all we have to do is just multiply all of this together. So now we'll just type this in. We have second up arrow here to pull up a pi. Then we have 38 squared. And we're going to multiply this by the fraction 102 over 360. So what I could do here is just write parentheses 102, and then I'm dividing by 360. And this will give us the area of the sector. So to the nearest square mile, we're going to round to the nearest whole number. We're going to get 1,285. And we're rounding down because if we look at the whole, well, the ones place here, we look to the right is a 3. We're rounding down to 1,285. And the units here are technically square miles, but once again, we don't actually have to write the units in our answer. So here's our solution to question 26. Question 27, we have segment CA is drawn below, and using a compass and straight edge, we want to construct isosceles right triangle CAT, where CA is perpendicular to CT and CA is congruent to CT. So for this question here, we just have to be very careful and make sure that we construct a right angle at the correct point. So if CA is perpendicular to CT, that means the right angle is going to be at point C over here. So the first thing I'm going to do is just extend this line segment here. So I'm going to go out like this because the technique that I want to use is constructing a line that is perpendicular to another line going through a specific point. So let's just pretend that I have a ruler and a pencil here, and I'm just extending through point C. So now I'm going to place the compass onto point C like this, and I'm going to swing an arc going in this direction here on the right of, or to the right of point C, and also to the left of point C. And now these 2 points here are going to be our points to help us find the second point for our perpendicular line. So I'm just going to extend the compass out a little bit, because if I don't extend it, it's just going to go right back to point C, and it's not going to give us a second point for our line. So now we're going to go ahead and swing an arc like this. We're going to swing the arc a little bit above C like this, and now we're going to move the compass over to the other point of intersection and repeat this process. So here we go. We're going to just once again swing the arc like this, and there's our point of intersection. So now we're going to go over to point C, which was originally here, and we're going to draw a line segment going through point C to that point of intersection that we just made. If you want to extend this a little bit more going through like this, you're allowed to do this here, but at the end, we just need to make sure that we define point T, and then we connect CAT to actually form the isosceles right triangle. So if I have to, I can extend this out a little bit more. So now, once again, we want CA to be congruent to CT. So the next thing I would do is measure the distance from point C to point A. So I'm just going to extend the compass like this, and I'm just going to mark like this just to show that I measured the distance from C to A. And now I'm going to move the compass up here and swing the arc like this. And now all we have to do is connect these 2 points. So we could draw in the line segment connecting these 2 points here. And then the last thing I'll do is just label this as point T. So here is our construction of isosceles right triangle CAT, and the right angle is over here at point C. Question 28, on the set of axes below, congruent triangles ABC and DEF are graphed, and we have to describe a sequence of rigid motions that maps triangle ABC onto triangle DEF. So for questions like this, one thing you have to be very careful with is you have to know which triangle is your pre-image and which triangle is your image. And in this case, I know that the pre-image is going to be triangle ABC because we're mapping triangle ABC onto triangle DEF. So for one, we just have to make sure that we're careful because we don't want to do something like writing a sequence of rigid motions to map this triangle onto this one. And then the next thing to be very careful of is you want to make sure that you're actually mapping the points to the corresponding points in the next triangle. So if they're telling you to map triangle ABC onto triangle DEF, notice that A shows up first in triangle ABC, and then D shows up first in triangle DEF. So that would tell us that we have to map this angle A onto this angle over here at D. So just be careful, because you might be tempted to just go up one and reflect, or if you go up one over one and reflect over the y-axis, you might make the mistake of mapping angle A onto angle F. So now let's think about how would we get this point over here at A. So this would be the point if we were to put coordinates here. This is the point 2, and then we have 1, 2, 3, 4, 5. So how do we get 2, 5 to land at, this is the point negative 5, 2? And if you know your transformations, you'll know that, oh, this is a rotation of 90 degrees. But me personally, I can't memorize those rules. So what I like to do is I take my paper, and I'm just going to use this copy of the graph here. And what I do is if I want to rotate 90 degrees, I take my paper and I physically rotate it 90 degrees like this. And then I look at my paper and say, okay, where did point A land? And notice here that point A landed over here at negative 5, 2. If we look at point F is at negative 1, 1, 2, 3, 4, 5, 6. And now look where C is. C is at negative 1, 1, 2, 3, 4, 5, 6. So it looks like rotating 90 degrees counterclockwise about the origin would map triangle ABC onto triangle DEF. Question 29, in triangle ADC below, line segment EB is drawn such that these line segments have these measures here. And we want to know, is triangle ABE similar to triangle ADC? And we have to explain why. So here we are looking at these two triangles. We're looking at the small triangle here and the big triangle. The problem right away, though, is that the triangles are not facing the same direction, which makes this question a little bit trickier to deal with. So what you could do is you could just draw over here, have the triangles facing the same direction. So I'm just going to flip triangle ABE so that A is over here, B is now over here, and E is over here. And now you could see that the small triangle is facing the same direction as the big triangle. So AB is 4.1 units long, and then we have AE is 5.6 units long. And now if I draw the big triangle again, so I'm just going to redraw it over here like this, and I find the entire side length, that's going to help us answer this question. So I want to find the entire length of AD, so I'm going to add these two numbers together. We're going to have 5.6, and then I'm going to add, we have 3.42. And I'll just put a 0 here as a placeholder. So now we have 0 plus 2 is 2, 6 plus 4 is 10, I carry the 1, and then I have 1 plus 5 plus 3 is 9. So this side over here is 9.02. So next we could find the length of side AC, so we could just add these two values together. So we're going to do 8.22, and we're adding 4.1. So from here, I'm just going to do the addition, and we have that this side is going to be 12.32. So from here, to show that these two triangles are similar, or to explore if they are, let's use the side angle side similarity theorem, which states that if we have two triangles and the two sides in each triangle are in proportion, so if we set up, let's say 4.1 over 5.6, I'm comparing the left side to the right side. If this is equal to 9.02 over 12.32, and the angle between the two sides is equal in both triangles, then we could say that these two triangles are similar. Well, right away we could see that angle A is going to be congruent to angle A because this is the reflexive property. These two triangles share angle A. So the angle between the two sides we have selected are congruent. So this is looking good so far, but now we just have to check if this proportion holds true. So let's type in this fraction. I'm going to do alpha y equals enter, and we're typing in 4.1 over 5.6. And then right after this, after we press enter, we're going to do the second fraction here. So I'm going to press alpha y equals enter, and we're going to do 9.02 over the denominator, we have 12.32. And now moment of truth. Notice that the ratios here do match, so we can say that these triangles are similar. So let's just record this information here. We have these two ratios are equal to 0.732, and then we have 142, 85, 71. And we just established that two pairs of sides are in proportion in both triangles, but we have to be careful here. Make sure to mention that angle A is congruent to angle A. Okay, in order to use side angle side similarity, we do have to state that the angles involved are congruent, the angles that are between the two pairs of sides that we selected. So we have this statement here, and we have to establish that angle A is congruent to angle A. And this I'll just say reflexive property in parentheses here, just to be safe. So we have reflexive property. And then from here, we could write our concluding statement. So now that we've established that the two pairs of sides in both triangles, the corresponding sides are in proportion, as well as the angle between them, we could say that triangle ABE, so we have triangle ABE, is similar to triangle ADC. And the reason here is by side angle side similarity. Okay, so by side angle side similarity, and this time I'll just write it out. So we have similarity. And this is a lot to write for 2 points here, but this would get us full credit. Question 30, we have to determine and state the coordinates of the center and the length of the radius of the circle represented by the equation given here. So for this question, we have to know how to complete the square. And we also have to know the general form for the equation of a circle. So anytime we have an equation like this, when we have x minus h squared and then plus y minus k squared equals r squared, this represents the equation of a circle where the center is at hk. So we have center hk and the radius is r. And I'll just make this a little bit neater. So we have the center is at hk and the radius is at r. So our goal here is going to be to get this equation in this form here. And the technique that we have to be able to use is completing the square. So when we're doing this algebra, the technique of completing the square, we have to be skilled at the main part of the technique, which is taking half of the b term, squaring it, and adding that value to both sides. So what I like to do first is get the x squared and x term, the y squared and y term on one side of the equation, and all the rest on the right side. So the constant here, 44, I'm just going to move this over. I'm going to go plus 44 on both sides. And now when I write out the next line here, I'm going to leave a space strategically. So we have x squared plus 16x. I'm going to leave a space here, and then we're going to have plus y squared plus 12y. I'm going to leave a second space, and now this is equal to 44. Okay, so I'm just leaving a space here and a space here. And the reason being, I'm going to complete the square. So the concept of the complete the square technique, once again, is you're taking half of the b term. So in the first case, we have the b term is 16. We're dividing it by 2 and then squaring it. If you're not sure of where that phrase b term is coming from, it's coming from if we have a quadratic in the form of ax squared plus bx plus c, the b term is the coefficient of x. Now, technically, I have to be a little bit careful here. I could only use this complete the square technique that I'm about to use when there's an invisible 1 in front of my x squared and my y squared. But notice that the equation they gave us, it was 1x squared and 1y squared. So this is going to work out fine here. So now we go ahead and work this out. So we're going to have 8 squared, and this is equal to 64. And then my next b term is 12. I'm going to take half of 12 and then square this. So this is going to give us 6 squared is equal to 36. So I'm going to add, for this first part here, I'm going to add 64 here, but whatever I add to the left side, I have to do the same thing to the right side. And then to take care of this second piece here, I'm going to add 36. But if I add 36 to the left side of the equation, I have to add 36 to the right side of the equation. So now we just simplify this here. And what we're going to have over here is this is going to factor nicely when we look for two numbers that have a sum of 16 and a product of 64. So if you think about the two numbers, the numbers are going to be 8 and 8. So we're going to write x plus 8 times x plus 8. And once again, these numbers are going to work because 8 plus 8 is 16 and 8 times 8 is 64. And then next, I'm looking for two numbers that have a sum of 12. And the two numbers also have to have a product of 36. So the two numbers here would be 6 and 6 because 6 plus 6 is 12 and 6 times 6 is 36. So I have y plus 6 times y plus 6. Just be careful here. Make sure to write the plus sign between these two. A common mistake is students will just leave this sign out. And now on the right side, I have I have 64 plus 36 is 100, plus 44 is 144. And now I just simplify a little bit more. We have x plus 8 squared, because I'm multiplying this binomial by itself. And then I have plus y plus 6 squared. You know you did the process right for completing the square when you wind up with a matching binomial, okay? What you're basically doing is you're turning this quadratic piece here, this x squared plus 16x, you're turning it into what we call a perfect square trinomial, okay? So these two trinomials here are perfect square trinomials because we could express them as the product of matching factors. And now from here, we'll just make this a little bit neater. We're going to identify the center and radius. One thing to be mindful of here is if your center is h, notice that it winds up as x minus h. So when you're going from the equation to the center, what you're going to do is just write the opposite. So here, our center is going to be at, instead of plus 8, we're going to have our x coordinate is minus 8. And instead of our y coordinate being plus 6, we're going to take the opposite, minus 6. And then to identify the radius, just be careful here. Make sure you take the square root of this number here because the equation is in the form of r squared, but the radius is just r. So another thing we have to think about is just the square root of 144, which is a perfect square. The square root of 144 is equal to 12. So we could just say that our radius is equal to 12. And this is going to tell us here, so we'll just write this a little bit neater. So the radius here is equal to 12. Or I could just say r equals 12. So we'll just say that r is equal to 12. And here is our solution to question 30. Question 31, in the diagram below, triangle SBC is similar to triangle CMJ, and we're told that cosine of J equals 3/5. And we have to determine and state the measure of angle S to the nearest degree. So S is over here, so we'll just go ahead and highlight it. So our goal is to find the measure of this angle. And one thing that jumps out is they gave us the ratio for cosine of angle J. So we have the ratio is 3/5. And just know, anytime you want to go from the ratio to the angle, you have to use the opposite function. So if I'm starting with cosine of J is equal to 3/5, the opposite of cosine is cosine inverse. So this will tell us that the measure of angle J is equal to, we would have cosine inverse of 3/5. If I really want to write out the algebra technically, what I'm doing basically is I'm doing the cosine inverse of both sides of this equation. So I'm doing cosine inverse of the left side, and I'm doing cosine inverse of the right side. And when I do cosine and cosine inverse together, these are inverse functions. They cancel out, and it gives us the measure of angle J. So that's the big idea in this question, the concept that we're using to solve for the measure of angle J. And then once we know the measure of angle J, that's going to tell us everything else we need. So let's type in this function here. And remember, we're finding our answer to the nearest degrees. So I'm going to press mode, and I'm going to switch from radians to degrees. For the geometry regions, you want to be in degree mode for the entire test. For the algebra 2 regions, that's when you have to switch over to radians. But just know, if you're unsure if your calculator's in radians or degrees and you have a TI 84 plus CE, it'll tell you at the top if it's in radians or degrees. Or you could just press mode once again and check just to make sure it's in degrees. So to get cosine inverse, we're going to press second cosine, and we're typing in 3/5. And now we press enter, and here's our angle. So to the nearest degree, the measure of angle J is 53 degrees. We're rounding to the nearest whole number. We're going to look over here at the 3 in the ones place, and to the right is a 1. So that's why we're rounding down to 53 degrees. And that's the measure of this angle over here. But remember, our goal was to find the measure of angle S. And one thing to be very careful of, don't say the measure of angle S is 53 degrees. It's very tempting to say this because J is in this top spot over here and S is in this top spot. But remember, the order of the letters in which they told you the triangles is very important. Notice that J shows up in the final position here in the third spot. That means that J corresponds to C. So this angle over here, angle C, is 53 degrees because when you have similar triangles, corresponding angles in similar triangles are congruent. Okay, the two triangles here are the same shape, they're just a different size. So since they're the same shape, that means their interior angles match. So if we want to find the measure of angle S, now all we have to do is just subtract 53 degrees from 90 degrees. Okay, or I could just do 90 minus 53, and I'll write the units at the end. So I'm going to borrow here and make this an 8, or I could just use the calculator to do the subtraction. But we have 10 minus 3 is 7. 8 minus 5 is 3. So this angle over here is 37 degrees. Okay, so the measure of angle S, we could say the measure of angle S is equal to 37 degrees. And here's our solution to question 31. So now we're moving on to the part 3 questions, and every question here is worth 4 credits. Question 32, Trish is a surveyor who was asked to estimate the distance across a pond. And she stands at point C, 85 meters from point D, and locates A and B on either side of the pond such that A, D, and B are collinear, which means these 3 points form a straight line. And then we have Trish approximates the measure of angle DCB to be 35 degrees. So this angle over here we could label as 35 degrees. And then we have next that Trish approximates the measure of angle ACD to be 75 degrees. So we have this angle over here is 75 degrees going from A to C to D. And what we want to do is determine and state the distance across the pond AB to the nearest meter. So for this question here, the reason why this is 4 points is we're going to have to use trig ratios twice. So the mnemonic that we're going to use here is SOHCAHTOA. And let's think about what we have to find, and then that'll tell us which of these trig ratios to use. So if we want to find the distance from point A to point B, what we're going to have to do here is find the length of this segment here, X, or I could say the length or measure of line segment AD. And then we're going to have to find the measure of line segment DB, and then add those two together. So we're going to have to use the fact that we have 2 right triangles here, and we're going to use that to find this distance. So now we'll just go ahead and get started and think, if we want to find X, notice that X is opposite of the 75 degree angle. So this side is opposite, and the 85 meter side over here, the CD, this is adjacent to the 75 degree angle. So when you hear opposite and adjacent, you should be thinking of the tangent function. And then notice in this triangle over here that Y is opposite of the 35 degree angle, and 85 meters is adjacent to this 35 degree angle. So once again, we would be using the tangent function. So now we could just set up our ratios. We're going to say tangent of 75 degrees is equal to, and then we have opposite is X over the side adjacent to the 75 degree angle is 85. And now to solve for X, we could just call this tan 75 degrees over 1, and we could just cross multiply, and we'll have X equals 85 times tangent of 75 degrees. And now we're going to do something very similar, but using the other right triangle. Now we're going to say tangent of the 35 degree angle is equal to opposite of the 35 degree angle is the side that is Y units long, or we could say Y meters long. And this is over the adjacent side is 85 meters long. But we don't actually have to write the answers in our solutions, as I mentioned before, or we could just write everything in at the end. So what we have here now is tan 35 over 1, and we're going to cross multiply. We're going to get Y equals, because we're doing Y times 1, and Y equals 85 times tangent of 35 degrees. So we are in degree mode, so we could just type this in. We're going to have 85 times tangent of 75 degrees, and we press enter, and then I'm going to go ahead and do this for the Y value here. Y is equal to 85 tangent of 35 degrees. And these are the 2 values that we need. Now, ultimately, we want to find the length of line segment AB. So we're going to do X plus Y. So I could just take these 2 values here. I highlight the first one and press enter. And then I'm going to write plus. I go up to the second value here and press enter. And this is going to give us our sum. So now we could just write everything out. We're trying to find the measure of line segment AB. So we're going to say AB equals, and we did X plus Y. So I could just say 85 tangent of 75 degrees. And then plus Y was 85 tangent of 35 degrees. And the reason why I prefer to write it like this is because 85 tangent 75 is this really long decimal, as well as 85 tangent 35. So I would rather just do the addition like this and then write the final result rounded to the nearest meter at the end. So we're going to have AB is equal to, and if we look here at our ones place is a 6, to the right is a 7, so we would round up to 377. So the distance across the pond to the nearest meter would be 377 meters. Question 33, a candle in the shape of a right pyramid is modeled below, and each side of the square base measures 12 centimeters. And then we have the slant height of the pyramid measures 16 centimeters, And the first thing we want to do is determine and state the volume of the candle to the nearest cubic centimeter. So for this question here, one thing we have to be very careful of is that when we go to find the volume of this pyramid here with the square base, we are going to use this formula 1/3 capital B times H, where capital B is the area of the base. But we have to be careful here and note that 16 centimeters is not equal to the height. This is equal to the slant height. So just make sure that you're not plugging this value into the formula. What you're going to have to do is consider the anatomy of this pyramid. So I'm just going to redraw it over here like this. So I'll just redraw the square pyramid. And what we have is, if we look inside the pyramid, so we look at the square base at the bottom here, then what we're looking for is the height of this square pyramid. So we're going to draw down this line here, and this line is going to go right to the center of the square base. And this is what we're looking for. This is our value H, or the height of our pyramid. So the next thing to consider here is this distance going over. Since we went to the center of the square base and the length of the side of each side of the square is 12 centimeters, this distance over here would be 6 centimeters. And the slant height is the distance going from the top of the pyramid along the face to this point over here. And this we could just say is 16 centimeters. So once again, we are looking for the height of the pyramid. So we have to solve for the value of H. And for this, I'm just going to draw the right triangle off to the side. This is the right triangle that we need. We have H, and we have 6, and we have 16. So we could use the Pythagorean theorem here. So we're going to say that 6 squared plus H squared is equal to 16 squared. And now from here, 6 times 6 is 36. We get plus H squared is equal to 16 times 16 is 256. And now we just solve for H. We're going to go minus 36 on both sides. And then from here, what we have is 36 minus 36 cancels. We have H squared equals, and if we do the subtraction here, we get 220. So now to solve for H, we just take the square root of both sides. And this tells us that H is equal to the square root of 220. And this we don't actually have to simplify to simplest radical form because we are rounding to the nearest cubic centimeter. And unless they say express your answer in simplest radical form, you don't actually have to simplify. You just have to do it when they tell you to for the geometry regents. So now from here, we're just going to plug in. We have the volume equals, and we're going to write 1/3. And remember, capital B is the area of the base. Okay, so this is the area of the base. But since we're dealing with a right pyramid with a square base, we're going to find the area of the base just taking the side length and squaring it. So we're going to do 12 times 12, or 12 squared. And then we're going to multiply that by the height, which is square root of 220. So now we just type in, we have 1/3. And I like to just write something like 1/3 in parentheses just to play it safe. And then we're going to multiply by 12 squared. And remember, in math, parentheses means multiply. And then next, we're multiplying by the square root. I'm going to press second x squared. And then we have 220 going on the inside. And this is going to give us the volume of our pyramid. So to the nearest cubic centimeter, that means we're going to round to the nearest whole number. We look to the ones place as a 1, and to the right is a 9. So we're going to round up to 712. So the volume would be 712 cubic centimeters. And for this one here, I'm going to write the units in because when we do the second part of this question, it helps to express the volume in terms of cubic centimeters. That way we could see how the units cancel out at the end. So next they're telling us that the wax used to make the candle weighs 0. So we have it weighs 0.032 ounces per cubic centimeter. And we're going to use this information, the density, to determine and state the weight of the candle to the nearest ounce. So the concept that we need for this question is that density is equal to mass over volume. Okay, so we have density is equal to mass over volume. And now for the interest of the geometry regents, we're going to say that the mass is the weight. Although when you take physics at some point, you'll see that mass and weight are actually two different things. But for the interest of the geometry regents, we're just going to say that we're looking for the mass. So we have density times volume. And now from here, all we have to do is just plug in. We're going to say that the weight of the candle is equal to, and we're doing the density is 0.032 ounces. I'm going to write OZ, and then per cubic centimeter, I'm putting over centimeters to the third power like this. And we're going to multiply the density by the volume. And the volume we just found in the previous section here was 712 cubic centimeters. So we're using our value from before. And now from here, notice the units cancel out. That's why I like to write the units in for questions like this. So you can see how the units cancel. And then to find the weight, all we have to do is just multiply these two values. So now we just work out this product. We have 0.032, and we are multiplying by 712. So we're going to multiply by 712. And this tells us to the nearest ounce, the weight of the candle is 23 ounces. So we'll just record our answer. We have the weight of the candle to the nearest ounce is 23 ounces. And once again, when we are rounding to the nearest whole number, we look to the ones place, and in this case is a 2, and we look to the right is a 7, so we're rounding up to 23. Question 34, in the diagram of quadrilateral ABCD below, we have AB is congruent to CD, we have AB is parallel to CD, and then we have segments CE and AF are drawn to diagonal BD such that BE is congruent to DF. And our goal here is to prove that line segment CE, so that's this line segment over here, is congruent to line segment AF. Now, for questions like this, the proofs, I like to start with the actual proof statement and then work backwards to come up with a strategy. So one thing that jumps out at me is that these two triangles here, that these line segments that we're trying to show are congruent, are part of triangle BEC and triangle DFA. So one strategy would be to show that these two triangles here are congruent, and then we could say that corresponding parts of congruent triangles are congruent. So just targeting this, that's the idea that comes to mind. But now if we think of the bigger strategy, one thing to prove here would be to prove that ABCD is a parallelogram, because they told us right away in the beginning that one pair of opposite sides are both parallel and congruent. And then once we have that this is a parallelogram, we could say all sorts of things about the angles on the inside as well as the opposite sides. But in order to get full credit, the first thing we have to write are the givens. Now that we've got the givens out of the way, we could start to prove that these two triangles over here are congruent. So now we have to come up with a strategy for how are we going to prove those two triangles are congruent. Well, since we have a parallelogram here, we could say that these pairs of opposite sides are congruent. So we could say that AD is congruent to BC. Another thing we could say here is since we have a parallelogram, we could say that these angles over here, I'll label this as angle 1 and angle 2, are congruent because we have alternate interior angles formed by parallel lines cut by transversal BD. So far what we have is we have a pair of angles congruent, we have these two sides here congruent, and we have these two sides here congruent. So notice here that side angle side is staring at us because we have two pairs of congruent sides, and the angle between the two pairs of congruent sides are also congruent. So that's going to be our strategy here, but we can't make any statements about parallelograms until we actually say that ABCD is a parallelogram. And we're able to say that this is a parallelogram because we have one pair of opposite sides are both congruent and parallel. They told us that AB and CD are both congruent and parallel. So now we could write our statement and reason. So now that we've established that ABCD is a parallelogram, we could now say that line segment BC is congruent to line segment AD. And all in the same statement here, we could say that these two line segments are parallel. So we could say that BC is congruent to AD, and we could say BC is parallel to AD. And we could use the same reasoning as before, that in a parallelogram, the opposite sides are both congruent and parallel. So the same way that we established that we have a parallelogram, we could use that argument to establish why these two line segments are both congruent and parallel. So when I write proofs, I like to keep track of what I've said so far. So remember, earlier we said the strategy was to use the side angle side postulate to prove that these two triangles here were congruent. And notice that in statement 1, we established that BE was congruent to DF. So this over here establishes one pair of sides as congruent. And then in statement 3, we said BC was congruent to AD. So this established a second pair of sides as congruent. So the last thing that we have to establish before we say these two triangles here are congruent is the pair of angles that are congruent. Now, me personally, I like to write numbers on the diagram so that when I actually have to write the statement, I could just say something like this. I could say angle 1 is congruent to angle 2. You can write it out with 3 letters, but I just find it's easier to write numbers there, and you could just say it with numbers. It's just a way cleaner way to make the statement. But now for our reason, how do we know that angle 1 is congruent to angle 2? Well, when we have parallel lines cut by a transversal, the alternate interior angles formed are congruent. That is why I had to make this statement here. If I didn't say over here that BC was parallel to AD, and then I try to say that angle 1 is congruent to angle 2, I would lose a point for not making this statement, because remember, alternate interior angles only work when you establish that the line segments involved are actually parallel. So that's just something we have to be very, very careful of here. So these two line segments here are parallel, and that allows us to write our reason for statement 4. So statement 4 just established that the pair of angles here are congruent. So now we're ready to use the side angle side postulate. So for the next statement here, we could say that the two triangles in the diagram are congruent. So we're going to say next in statement 5 that triangle, and we have, let's say, BCE. So I'm going to say BCE is congruent to, and when I write out the next triangle, I just want to make sure that I'm writing the letters in corresponding order. So I went from B to C to E, so that would be correct then for us to say triangle DAF. So we'd have triangle DAF. And now this I just know works because this angle here at B, the one that we labeled with the 1, matches up with this angle over here that we labeled with number 2 here. So B and D correspond, and we could also say that A and C correspond, and then we could say F and E correspond. So now everything's in the right position. And the reason here is the side angle side postulate, but we could just write SAS. But now that we've established that both of these triangles are congruent, we could make the final statement here and say that line segment CE is congruent to, we have line segment AF. Okay, so this is true because corresponding parts of congruent triangles are congruent. And if this is tricky to remember, there's a nice funny way to remember this. You could also remember constipated people can't take craps. Okay, so whichever one helps you, then great, but just make sure you write CPCTC when you're saying that corresponding parts of congruent triangles are congruent. So now we're moving on to part 4, the final boss, and this question is worth 6 credits. Question 35, we have quadrilateral math has vertices with these coordinates here, and we want to prove that quadrilateral math is a trapezoid. And for this question, we're going to use the set of axes on the next page to plot these points. So now that we have these points plotted and connected, it's very obvious that the pair of sides that are parallel are MA and HT. So in terms of proving that we have a trapezoid here, we're going to show that these two line segments here are parallel by finding the slopes of these two line segments. And to show that two line segments are parallel, we just have to show that these two line segments have equal slopes. And the concept we're going to use for slope is we're going to say that the slope is the rise over the run. So here I could just count the rise over the run, and we could say that the slope of, let's say, line segment MA. So I'm going to write the slope of line segment MA. I'll just make this as neat as possible. So we have the slope of line segment MA is equal to, and the rise over the run, we're going down 1 to the right 2 to get from one point to the next. So our slope is going to be -1 over 2. We could use the slope formula, m equals y2 minus y1 over x2 minus x1, and just plug these points into the formula. But when you have a graph, the rise over the run is a great option to get the slope of the line segment. But let's say that we wanted to use that formula over here. Point H is located at -6, -3. And point T was located, or is located, at 2, -7. If I plug these points into the slope formula to find the slope of line segment HT, I could say the slope of line segment HT is equal to, and now I'm just going to call this x1, y1, and I'll call this point over here x2, y2. So if I plug into the formula, we're going to have -7 minus -3 divided by, and then we're dividing by x2 minus x1, so 2 minus -6. And now this is going to simplify to -7 plus 3 is -4 over 2 plus 6 is 8. So the slope of line segment HT is equal to -4 over 8, which reduces to -1/2. And notice that these slopes are equal in measure, which tells us that these two line segments here are parallel. And for the geometry regions, all we have to show is that we have one pair of parallel sides. And then this is enough for us to establish that we have a trapezoid. We don't actually have to go through the trouble of showing that these two slopes here are not equal in measure. But just so you know, there are some geometry tests or other parts of the world you're going to learn geometry that you would have to establish that these two line segments here are not parallel, because in some places a trapezoid will be defined as a quadrilateral with exactly one pair of parallel sides. So then you would have to show that these two sides here are not parallel, but for the geometry regions we only have to show that we have one pair of parallel sides. So we'll just use this work to write out our solution. So we're going to say over here in the workspace that the slope of line segment MA is equal to -1/2. And we're going to comment here that the slope of line segment HT is also -1/2. And what we could do is we could just write lines here, or we could draw lines like this and say that, hey, these are equal. So these are equal, which tells us then that the line segments MA and HT are parallel. So you are allowed to abbreviate like this and use symbols, kind of like a flow chart to say what you need to. So we've established that one pair of opposite sides are parallel. So that establishes here that math is a trapezoid. So now we want to state the coordinates of point Y such that point A is the midpoint of line segment MY. So if we want A to be in the middle of MY, we could see using this space over here that Y is going to be somewhere in this neighborhood. And for precision, we're going to go down to this workspace over here, and we're going to calculate the rise over the run to get from point M to point A. So to get from M to A, we have to go down 2. So we're going down 2, and then we're going to go over 1, 2, 3, 4. So we're going down 2 over 4. And now I'm just going to repeat this. I'm going to go down 1, 2, and over 1, 2, 3, 4. So this would be the visual way to find the location of point Y. And you could even see that if Y is over here, A is definitely in the middle of these 2 points, M and Y. And now we just have to identify the coordinates of Y. So we're going over 1, 2, 3, 4, 5, 6, 7, and we're going up 1, 2, 3. So the coordinates of Y would be 7, 3. Remember, when you're identifying the coordinates of a point, you have to start at the origin. So that's where this is coming from. And now I'm just going to write the answer in our space up here. So the coordinates of Y, we're going to say are 7, 3. Now for this one, if we want to check our work, what we could do is we could use the points that we started with here. We started with knowing that point M was located at, we have -1, 7, and point Y we're saying is 7, 3. So if A is the midpoint, we could use the midpoint formula, the x1 plus x2 divided by 2, comma y1 plus y2 divided by 2 formula to see if point A is actually in the middle of MY. So we're gonna have here A is located at, and now we're gonna add the x value of M and Y. So we're gonna have -1 plus 7. So we have -1 plus 7, and we're dividing this by 2, comma, and now we add the Y values. So we're gonna add 7 plus the Y value here is 3, and we divide by 2. Now this simplifies to, we would have -1 plus 7 is 6, divided by 2 is 3. And then we have next to it, after the comma, 7 plus 3 is 10, divided by 2 is 5. So A should be located at 3, 5, and notice that A is located at 3, 5. So this point here for Y is definitely good. So now for the last part of this question, we want to prove that quadrilateral myth is a rectangle. So if we go down here and look at what we have, to build rectangle myth, I'm just going to connect point A to point Y, and then I'm going to connect point Y to point T. And now our goal is to show that this shape here is a rectangle if we go from M to Y to T to H. Well, so far we found the slope of these two line segments, so we could continue and use that strategy of using slope to show that we have a rectangle. So the extra thing we would have to do here is find the slope of line segment MY. So I'm just going to find the slope of the entire side. But if all we did here was continue line segment MA to build line segment MY, we could just say that the slope here is also negative half. I could calculate the rise over the run. I'm going down 1 over 2 repeatedly to get from point M to point Y, so that's our slope. Or I could use the slope formula that I wrote down before, but we can just say here that the slope of my is equal to negative half. And now next we'll find the slope of this side over here. We'll find the slope of line segment TY. And for this line segment over here, so we'll just make that a little bit neater. So we're finding the slope of line segment TY. We're going to calculate the rise over the run, and we're going up 1, 2, and over 1. So we're going up 2, over 1. So the slope is 2 over 1, or we could just say the slope is equal to 2. And then next we'll find the slope over here. The slope of line segment HM is equal to, and if we calculate the rise over the run, we're going up 2 over 1. So we get a slope of 2. So notice here what we have is that these pair of sides over here are also parallel because they have the same slope. So right now we have a quadrilateral where both pairs of opposite sides have equal slopes and are therefore parallel. But another thing to notice here is when you think about the slopes that we have a slope of 1 over 2, or negative 1 over 2, I should say. We have a slope of negative 1 over 2, and we have a slope of positive 2. These numbers here are opposite reciprocals. Okay, to get from negative 1 over 2 to 2, I would just change the sign here from negative to positive, and I would flip this fraction to 2 over 1 to build this number here. So these are opposite reciprocals, which tells us that we have right angles here. So I could say I only have to show that one angle is a right angle, so maybe we will focus on angle Y. But once we show that we have a parallelogram because both pairs of opposite sides are parallel, and then we show that we have a right angle, we could say that myth is a rectangle because it is a parallelogram with a right angle. So now that we have all of this information down, we commented that our opposite sides have equal slopes, which makes our opposite sides parallel. And we also commented here on a single pair of consecutive sides that the slopes are opposite reciprocals, which makes the two line segments perpendicular, telling us that in this case, if we're targeting angle Y, that angle Y is a right angle. So now we could just write our conclusion. Since both pairs of opposite sides are parallel, that tells us that myth is a parallelogram. And since the parallelogram has a right angle, that makes the parallelogram a rectangle.